we're going to get into chapter 7 today. And we're going to go a little bit out of order from how chapter 7 is set up. I think it makes a little bit more sense if we talk about the chemical reactions first, and then we get into the calculations regarding chemical reactions. So we're going to kind of do the second half of chapter 7 first, and then go back into the first half. So if you're following along in the book, that might be a little weird, but hopefully it'll work out. So chemical equations, what are those? Well, they're just a way of expressing a reaction. And we've already kind of dealt with some chemical equations from lab and from just like things popping up here and there. But a chemical equation is a way to write down what happens in a chemical reaction. Okay, so let's take one, for instance, one that we've seen. Hydrogen and oxygen make water, and they're reacted together. Other things that we often see in a reaction like this, the state of the reactants and products is often labeled. So you might see a little G in parentheses, which denotes that the reactants are gases. And in this reaction, actually, everything is a gas. So the product gets a gas as well, gets a G as well. There are 4 different little labels that you'll see for those states. They are S, L, G, and AQ. S is for solid, L is for liquid, G is for gas, and AQ, which is kind of the weird one, it's not really a state, but it means aqueous, which is a solution in water. We'll just say dissolved in water. So something that was dissolved in water, and then you use it. Like all those test reagents that we used in lab on Tuesday, those would all have an AQ if we were going to write out those equations. AQ for being dissolved in water. Okay, other things about a chemical equation. The left side is what you start with. So the things on the left side are known as the reactants. And whatever's on the right side is the products. In this case, there's 2 reactants, 1 product. There's an arrow in the middle that shows reactants going to products, but that arrow isn't always going that direction. We're going to see some reactions that go both ways, that can go back and forth. And in those cases, we might draw an arrow going the other way, or we might actually draw both arrows going on top of each other, like one going one way and one going the other way, showing that both of those things could happen. So sometimes those definitions will switch depending on the arrow, but for the most part, we're going to see our reactants on the left and an arrow going to the products. Okay, so there's a problem with this equation so far. Anybody see it? Yeah, the way that it's written right now shows something happening that cannot happen. So if we imagine this from the structures, remember we were drawing some structures and some bonds and stuff the other day. H2 is H, like that. O2 is O. Remember they share 2 pairs of electrons in that one, so they have a double bond. So then H2O is HOH. But if that's actually true, then what's happened in the course of this reaction is that 1 oxygen has simply disappeared. It's gone, not there anymore. That can't happen. Anybody know why that can't happen? Yeah, mass can't be created or destroyed. It's called law of conservation of mass. In a chemical reaction, you can't just destroy mass, nor can you create it. A long time ago, people thought that you could, that when you like burn something, it was actually gone. Now we know not actually gone, right? It's just converted into a different form. It's now a gas instead of whatever it was before. So we know now that in a chemical reaction, you don't actually destroy atoms. So how come this reaction that I've drawn shows us destroying an oxygen atom? What's wrong with it? Did I write one of the reactants wrong or something? Should I have just written O instead of O2? No, we know oxygen is O2. Everything's okay. Maybe, so we need to fix it, I guess, is the answer. We need to fix it. We can't have an equation where you have atoms disappearing on one side or the other, or appearing. They have to be the same on both sides. So how are we going to do that? Can we put a 2 down here and say, okay, instead of H2O, it's H2O2? Why can't we do that?
Because it would no longer be water, it'd be a different molecule.
Yeah, does anybody know what that molecule is, what H2O2 is? It's hydrogen peroxide. Is that the same thing as water? Hopefully you don't think that that's the same as water. Don't drink hydrogen peroxide. Yeah, it's not water. Definitely not water. So when we change the little subscript numbers, we change the identity of the compound, of the chemical compounds. So that's not a way we can fix it. Anybody think of another way we can fix it?
Have like a different number of molecules, so you can have like 2
Right.
H2O and 2 H2.
Right, so we're gonna need, what this is really saying is that we have not adequately expressed or accurately expressed the ratio in which these things react. So we're saying one hydrogen molecule and one oxygen molecule come together and make one water molecule. But that's not actually how it works. We know that's not how it works because we would get rid of an oxygen and we can't do that. So we need to come up with another way that we can show hydrogen and oxygen reacting, but in another ratio so that we don't lose stuff like that. So if we said that we have 2 hydrogen molecules instead of just 1, and then we say that we're going to make 2 water molecules instead of just 1, that fixes our problem, right? If we look at those atoms now, we've got 4 hydrogen atoms on the left, 4 on the right. 2 oxygens on the left, 2 oxygens on the right. So everything's good. We're no longer destroying atoms or whatever we were doing before. So that's how we fix this. We adjust the ratios so that everything balances out and we have the same number on each side. And to express that in the equation itself, we put big numbers out front for the ones that we're adjusting. So we would say 2 H2s react with 1 O2 to make 2 waters. Okay. So that's really a complete chemical reaction. And those numbers that we put there are called coefficients. And that tells us how many of each thing we have. So when we write down a chemical reaction, we have to adjust the coefficients to get them to balance, to get all the atoms to equal each other on both sides. It may not be immediately obvious how to do that. Like if you're just looking at something, how did I know that I needed 2 of these and 2 of these? So that's what we're going to do next. We're going to talk about how do we do that. The act of doing that is called balancing chemical equations. And if you've learned some way to do this in past classes or something that works for you, that's great. Stick with that. This is the way that I do it. If you like this way, great. Okay, I'm going to write down some reactants and products that are not balanced. And we're going to talk about how we bring them into balance. I should note also, the little states that we talked about, gas, aqueous, solid, a lot of times you can't know what they are just writing down an equation. So if I just told you hydrogen reacts with oxygen to make water, write that down, I wouldn't expect you to know if that was gas or liquid or solid or what. That you would have to be told that in general. Sometimes you can kind of figure it out, like if it says hydrogen in a balloon reacts with something in the air, you can assume that's probably a gas, but you can't always know. Okay, so here's our reaction. We don't know if it's balanced yet or not, and that should be your mindset when looking at any reaction, especially on an exam or a quiz. Don't assume it's balanced, don't assume it's not balanced. Check for yourself. It's not going to say the unbalanced equation below, sometimes maybe, but not all the time. So make sure you're always checking that. So how do we check it? You just count. What I like to do is count up the atoms or the different types of each atom and just make a list. So we might have like Fe, S, H, and Cl on both sides. And then I'm going to write how many of each we have just by counting them up. So I've got 2 Fe's, 3 S's, 1 H, and 1 Cl on the left. Over on the right, I've got 1 of these, 1 of these, 2 of these, and 3 of these. So now we can see pretty clearly this is not balanced. The numbers are different on each side. So to bring them into balance, what you do is pick one. Doesn't really matter which one. We're going to see a couple examples where it does matter, but before we get to that, but in general, it doesn't really matter. Pick your favorite and change a coefficient to bring it into balance. So let's say we picked iron, because I wrote that down first. We've got 2 on the left and 1 on the right. So we want to figure out how to get 2 on the right. So what would we do? How can we change a coefficient so that we have 2 on the right to balance with the 2 on the left?
Can you just write it there?
Yep, you just write it there. So we're going to put a 2 here to show that there are 2 of that whole unit. But when you write that number out front, you have to remember that that applies to the entire thing that you're writing it in front of. So the next step should always be that you readjust your quantities underneath now that you've changed something. Because now we have 2 Fe's instead of just 1. But we've also changed the chlorine. Instead of 3 now, we have 6. Because we have 2 of that entire unit. So we now have 6 chlorine instead of just 3. All right. So now we pick another one and do the same thing. What I like to do is whatever one I just changed, that's the next one I do. You don't have to do it that way. That's how, just that way I don't forget one. So we changed the Cl. So let's try to bring those in balance. We got 6 on the right, 1 on the left. So I'm going to put a 6 up here to bring that into balance and then readjust everything. So 6 of these. And I've also changed the hydrogen, so I have to make sure that I also correct for 6 of those. Okay, that messes with my hydrogen, so maybe we'll do that one next. Hydrogen, there's 6 on the left and 2 on the right. So what do I do to bring those into balance? Put a 3, right. So we're going to put a 3 over here. That changes my hydrogen to 6 and my sulfur to 3. Then I look at the sulfur and say, oh, okay, it's already done. So that last change actually brought everything into balance. And now we can say this is a balanced equation. Assuming you've counted everything properly, you should never get these wrong because either the numbers will match up or they don't. Unless you counted wrong, either the numbers add up on both sides and they're equal on both sides or they don't. So any questions about that procedure? No? Okay, let's try some more. So sometimes some other little weird things come up. We're going to try a few different ones to look at that. This is a combustion of butane. It's a little weird. Butane is reacted with oxygen to make carbon dioxide and water. Those are gases too. All right, so first let's list our stuff. We've got on the left C, H, and O, and on the right C, H, and O. We add them all up, and we've got 4 C's, 10 H's, 2 O's on the left, 1 C, 2 H's, and 3 O's on the right. So in this case, we're going to go through it the same way, but there actually is an importance to the order. And this is a trick that can help you out. If a particular atom is in 2 different molecules on the same side, save it to last. So oxygen is in both products. So we're going to save that one for last. Then you have to kind of play with it and see. Yeah, it doesn't come up a lot. But yeah, sometimes you can figure it out from other clues in the reaction. But usually there's one that's like obviously save it till last. Like it's in everything, or it's in at least a couple on one side, something like that. So if you see that, you save it to last. And the reason is this. We don't, because it's in 2 different ones, we know we're going to be changing the ratios around to get everything in balance. So if we look for that one first, there's a good chance that's going to change by the time we get later in the balancing process. So we're just going to save that to last. All right. So now I want you to do this one the same way that we did the previous one. See if you can do it on your own. And you might find that you run into a little problem. If you come up with a way to get around that problem, go for it. If not, just stay stuck at the problem, and then we'll talk about it together. All right, did anybody get stuck? Or you can't get it to balance? So let's go through it. So if we go through that same process, I see there's 4 C's on the left, 1 on the right. So I go with 4 here. That changes this to 4, changes this to 8 plus 1 is 9. Yeah, so far? Okay. Then I see that there are 10H on the left and 2 on the right. So I can go 5 here, get my 10H, and that changes my O again to 8 and 5 is 13. Okay, now everything works. I just got to get 13 O's on the left. How do I do that? Doesn't work, right? Because you've got an O2 on the left, so I can only get multiples of 2 on the left, so I'm not going to be able to get an odd number. So what do we do? How do you make odd numbers into even numbers? I mean, there's a few ways, but you can like add an odd number. But importantly for us is it doesn't really matter what those numbers are that we put in the equation. What matters is the ratio. Those numbers tell us that these things are reacting in a particular ratio. So that means that we can take multiples of those numbers and still have the same right thing. And that's exactly what we do. So when you run into this problem, you double everything. And that should get rid of your odd numbers. So instead of 1 C4H10, we're going to go with 2 C4H10s. That changes this to 8 and this to 20. And then the other ones, instead of 4, we're going to go 8. Instead of 5, we're going to go 10. So that changes this to 8 and this to 20. And it changes the O's from 13 to 26. So we've doubled everything. Now we can do this because 26 is an even number. So O2, what number do we have to put in front of O2 to get to 26? 13, right. So that's going to change this to 26. And now we have a balanced equation. So you see how that worked? That's something that comes up a lot. When you have an odd number on one side, even number on the other side, and you can't get them to balance, try doubling everything, and you can do it. The other thing that you probably notice here is a lot of crossing out stuff. This is definitely a trial and error type process. You can't always just balance something by looking at it and deciding what numbers go where. Sometimes you can, but usually you can't. So you go back and forth. You try stuff, you move numbers around, and sometimes it takes a little work, it takes a little crossing out, it takes a little erasing. Eventually you get to those numbers that balance. If you're doing if you're trying to do this to a reaction and you notice that the numbers are just going crazy, like you go from one side, you balance the other side, then you balance the other side, then you balance the other side, then you balance the other side, you balance the other, and like they keep going out of balance, something's wrong. Probably you wrote a number down wrong, like you wrote CO3 instead of CO2 or something like that, or something else happened. If it keeps going crazy like that and you just cannot get them to balance, chances are there's something wrong with the reaction in the first place. A big thing that goes wrong is not writing the formulas down correctly, which can certainly affect this. So let's try that. A lot of times you won't get a reaction written like I've just written them. You'll get a reaction like this. Sodium phosphate reacts with magnesium chloride to form magnesium phosphate and sodium chloride. Okay, so see if you can write a balanced equation for that reaction. All right, you got an equation for this one yet? Still thinking about it? Maybe. So notice that, as you probably are noticing, that if you write down the wrong formulas for any of those compounds, the chances are the equation's not going to balance right either. You might get it to balance, but it might not be right. And as we'll see, and I would probably get to it today, but as we'll see next week, if the equation isn't balanced properly, all the calculations and things that you need to do with that equation end up getting screwed up. So when I emphasize that like the naming stuff is really important, this is one reason it's really important, because it kind of goes with everything else. And so we'll see some problems coming up next week where like you have to get this part right or everything else ends up getting messed up. So let's take a look at the equation. The equation itself is going to look like this. These are all aqueous solutions, by the way. Doesn't matter if you knew that or not. The balancing and the formulas are the important part. Magnesium phosphate is solid, it's not soluble. Sodium chloride. Okay, so there's our equation. Take a look at what you got. See how your equation compares to that. It's not balanced yet, but see what you think. Okay, if that's not what you got, please go back and review those naming rules and practice naming compounds and writing down compounds from names. I should say in this particular example, writing the compounds from names is more important than being able to name them. Okay. To balance this, when you have these kinds of equations, there's a nice, not really a trick, but a nice thing you can do. The PO4, right? PO4 is phosphate ion. That doesn't change in the course of this reaction. The phosphate ions on the left become the phosphate ions on the right. They switch partners, but they don't change yet.
Isn't magnesium phosphate Mg3?
Oh, yes, you're right. I'm sorry. I was going to say this doesn't look right. I guess I should take my own advice and go review this stuff a little bit better. Is that what you're saying? Yeah, thank you. Sorry, I didn't always get that one. Mg3PO4 2. So anyway, the PO4s on the left are the same as the PO4s on the right. So they don't change in the course of the reaction. So that means that one thing that can be helpful, especially if there's a bunch of these kinds of ions around, is to list that as one of your things that you're counting instead of listing the P and the O separately. It's just less to count. So if I'm doing the inventory of these things, I might go Na, PO4, Mg, and Cl. On the left, I've got 3, 1, 1, and 2. 1, 2, 3, and 1. Okay. Now we start going back and forth to balance. So sodium, I'm going to get 3 over here, which gives me 3 of these and 3 of these. If I go to do the CLs now, what's going to happen? We got that same issue, right? So one thing you can do, there's a couple choices here. So you can first just skip it because we've got other stuff to balance. Or you can try to bring them into balance by going like 2 and 3. I would say for now, let's just skip it. Let's see what happens with the other ones and come back to it. So PO4, 1 on the left, 2 on the right. So I need 2 of those. That also changes my sodium. So my first sodium is now out of balance too. So I should change that to 6, which gives me 6 of these and 6 of these. Okay. And that kind of fixed my chloride problem there. So now 2 CLs on the left, 6 on the right. So I'm going to need a 3 here to fix that. And that also fixes my Mg, and now everything's in balance. So if I had continued to write that, leave that wrong and leave it as just MgPO4, I don't think it would have balanced. It might have wrongly, but it would have been hard to balance at all, I think, in this case. So it's important you get the formulas right when you write them down. Okay, questions about that kind of thing? All right, we will do a little bit more practice of this, hopefully. But let's move on. The last part that we're going to do today is, and this is going to come up in lab on Thursday or on Tuesday next week, is the types of reactions. People always like to categorize things, and this is part of that, just kind of to have stuff be in categories. But there's a purpose here also. Chemical reactions are sometimes really easy to predict, sometimes impossible to predict. That's why we have to actually do experiments to figure stuff out. But for the experiments we're going to see, if they fit nicely into one of these categories, we can probably at least have a pretty good guess as to what the product's going to be. And so that's what's powerful about this categorization that we're going to see, is if you can take a reaction that you haven't seen before and fit it into one of these categories, you can actually figure out what it's going to make, or at least make a good guess as to what it's going to make. So on Tuesday, we're going to do one reaction from each category. And then you'll kind of get to see what those look like. And then you should be able to place some of these reactions in these different categories after we've done that. Okay, so let's go through the types and what they look like. So first type is called combination, or sometimes composition. And this is where you're combining a couple things together to make one product. So you've got a reaction of the type A plus B yields AB. That's called a combination reaction. Sometimes it could be A plus B plus C equals ABC. And A and B can be whatever. They can be large compounds, they can be small compounds, but you put things together and they just end up making one product. That's called composition. An example of that is one we just did earlier. Hydrogen and oxygen. So that'd be a composition reaction. Oh, these are sometimes hard to predict because they just look like two things reacting. So if you didn't see the product, how would you know that they just go together? One key is combination reactions often happen with the elements in their elemental state. So like hydrogen and oxygen with nothing else connected go together. If it's two different things that have like multiple parts, chances are they're not just going to go together. They're going to do something else. So another example is, let's say I told you, and this is a reaction that you're going to do on Tuesday, magnesium reacts with oxygen gas, and we want to predict the products. So one thing we might say here is, well, magnesium is an element in its elemental state. Oxygen is an element in its elemental state. So if these two things are reacting together, probably they form a compound together. But what's important to remember is it doesn't mean you just smash the things together, because we have to deal with ratios and stuff. So we say, there's probably going to be some product made out of magnesium and oxygen. What would that product look like? So what do you think that would look like to have a compound made out of magnesium and oxygen? What do you think its formula would be?
Magnesium oxide.
Magnesium oxide, right. So what's the formula for that?
MgO.
Right, MgO. It's tempting to see that Mg plus O2 and say, oh, it just makes MgO2. But that's not the compound for magnesium and oxygen, because we know oxygen makes a 2- ion and magnesium makes a 2+ ion. So when they come together, they're making a 2+, 2- pair, so they just need one of each. Okay? So that means now that this reaction is not balanced and we need to fix it. So that's another composition reaction. Okay, second reaction type. kind of the opposite. Decomposition. Things breaking apart. This one's really easy to see because it's the only type that just starts with one thing, because it's literally just what we just had backwards. So it's AB becomes A and B. This one is probably the hardest to predict the products on, because, and by hardest I don't mean like requires the most studying or something, just like sometimes you just can't know. Because if something breaks apart into various pieces, you don't necessarily know which pieces it's going to break apart into. The one we're going to do on Tuesday is this one. Calcium carbonate, solid. When it's heated, it decomposes. So we can see that pretty clearly. If I didn't tell you the products, I could say, oh, well, that's definitely a decomposition reaction, but what's the decomposition? What breaks apart? Does the Ca break away from the CO3? Does the Ca and the C stay together and the O goes separately? Like, there's not really a good way of knowing that, at least as far as we're concerned. So it's hard to predict those kinds of things. The actual products are calcium oxide and carbon dioxide. Carbon dioxide gas. So that's one where we might have to do an experiment and then actually see what we have left over or see what happens and use that to figure out what it was. The third type are the ones we're probably going to see the most. And those are the replacement reactions. And there's two types, so we'll look at them separately. The single replacement and the double replacement. Single replacement takes this form, something by itself, some element by itself, plus a compound, something with two things in it, switches. And one of the pieces of the compound ends up by itself. The one we're going to do on Tuesday is solid zinc reacting with HCl. Okay, so before we draw the products, let's look at what's happening here. Zinc is by itself, that's this A, and then HCl is the compound, the BC. So we would expect the zinc to end up with one of those H or Cl, and the other one to end up on its own. So what do you think the zinc is going to end up with, the H or the Cl? The Cl, that's right. Why? How'd you know? Or was it just a guess? What?
Hydrogen's a gas.
Because hydrogen's a gas. Yeah, so that could be a way for this reaction to go forward. Yep. The other thing is we know metals usually go with like the nonmetal, the most nonmetal thing. And hydrogen's technically a nonmetal, but a metal hydrogen compound is a little bit special, kind of reactive, not something we see a lot. So we see things like metal chloride compounds all the time. So we could just guess, and again, it's a guess, but it's a good guess. We would guess that the metal is going to go with the chloride just because that's something that happens a lot. And I could say, haha, I tricked you, it actually goes with the hydrogen, because there's always stuff like that in chemistry, but in this case, we're good, and our guess is right. So the zinc goes with the chloride, and hydrogen goes off by itself. Now notice a couple things we had to be able to do to solve that. First, we had to know that when hydrogen goes by itself, it's not just H, it's H2. Because it's in that list that we talked about last week of the molecular elements. Second, we had to know that zinc was 2+, would make a 2+ ion, which we didn't really talk about, so don't worry about that. But in general, remember you got to make a new compound even when the things switch places. So this is now not balanced. We would put a 2 here to balance it. Our next part is double replacement. And this is usually going to occur when you have two ionic compounds reacting together. The A-B type notation, which can be a little bit confusing, it's not necessarily helpful, but that's how it's usually discussed. Think of those as ionic compounds, cation, anion, cation, anion. The cations and anions switch places. So the cation from compound 1 goes with the anion from compound 2, that's the A and the D, and then the other ones come together also. That's what we mean by double replacement. They switch partners. The cations and anions switch partners. This is all, yeah, this is pretty much always going to happen with ionic compounds. And the only trick to this one is, remember, when they switch partners, you have to recalculate the appropriate formula based on the charges. So let's try an example. Barium chloride and sodium sulfate. We should be able to see that as a double replacement because you've got two ionic compounds, cation, anion, cation, anion. So they're going to switch partners, which means the barium is going to go with the sulfate, and the sodium is going to go with the chlorine. So barium with sulfate, and sodium with chloride. Now we have to make sure that the charges match up. So what's the charge on barium? Number 56. 2 plus 2. And what's the charge on sulfate? Minus 2. So plus 2 minus 2. Barium sulfate is going to be just like this, right? That's actually a solid. And what about sodium and chloride? What's the compound that those make? NaCl. Other people knew that, right? Also? Okay, good. Okay. So when I ask these kinds of problems, it's not uncommon for somebody to realize that this is a double replacement reaction and write BaSO4 and Na2Cl2. But sodium chloride is not Na2Cl2, it's NaCl. So make sure that you are recalculating your formulas as you switch partners when you're doing these types of problems. All right. This is not balanced, so we have to put a 2 here. What's that? All right, those are the replacement reactions. Questions about those? Remember that the point of these, and we're not going to do too much of this just because it's hard and it doesn't always work, but the point is predictive ability. That if you can put a reaction in one of these categories, you can predict what the products are that it's going to make. That's the goal anyway. Okay, our last category. Well, there's another one too, but I don't know if we'll get to that. It's called combustion. And combustion reactions are, well, combustion in general refers to reaction with hydrogen, or sorry, reaction with oxygen. And we're usually going to use this term to apply to a class of molecules called hydrocarbons. Hydrocarbons are molecules made from carbon, hydrogen, and sometimes other stuff like oxygen. But mainly, the important part is the carbon and hydrogen. That's where hydrocarbon comes from. So most of the combustion reactions we're going to see are going to be a carbon-hydrogen type compound reacting with oxygen. Like this, like the one that we balanced earlier. We'll try another one. CH4 is methane gas, and that can react with oxygen gas. Combustion reactions are nice because when you recognize them, they only ever make the same products. When you see that hydrocarbon reacting with oxygen, you know your products are always going to be CO2 and H2O. Doesn't matter what hydrocarbon you use, always going to form the same ones. So this is not balanced. We've got a few more minutes left, see if you can balance it. All right, let's get this balanced, hopefully. Let me show you how I do it and how hopefully you can do this balancing as you get better and more practice at it, rather than writing down all the inventory and stuff, which is a great way to do it, by the way, because you're more likely to get it right. But another way you can do it is just kind of bounce back and forth across the reaction. So you can say like, okay, carbon 1 and 1, so those are good. Hydrogen 4 and 2, so I got to put a 2 here. Oxygen 4 on this side, 2 on this side, so I got to put a 2 there. You kind of go back and forth that way and get them to come into line. If it's a really big messy equation, you might still want to put down all of the different steps, but that's one way to do it too. Okay, so those are the types of reactions. On Tuesday, we will do a lab where we see all these reactions, and then on Tuesday we'll also do stuff about using these reactions to do certain types of calculations. And then on Thursday, we'll do a quiz. So keep working on the homework. And yeah, have a good weekend. Apparently there's cheap coffee today at Dunkin' Donuts, someone told me.
66 cents.
66 cents? All right, so go there if you need some coffee.